Howdy, my name is Shreeman Kuppa Jayaram, and I am a senior computer engineering student doing URS project with Dr. Yang Shen in the ESN department. My project name is Molecular Discovery Chatbot, and today I'll be presenting the final demonstration. I'll begin the final demonstration with a showcase of how the chatbot and the visualization system works. The chatbot subsystem was designed using Streamlit, which allows efficient connection of the large language model with the front end and other visualizations and other subsystems. I defined two different pages, the chatbot and the database page to navigate to from the landing page. For the chatbot page, I created a model and I called this function which would execute the entire page. So to show you what I mean, the create model function takes in temperature, k-value, and max tokens, and it passes it to the model. In this case, I set the default 0.01, 128, and allowed up to 4,096 tokens to be accepted as a prompt for the model using this parameter. I set up a memory to store the chat history so that we can allow for sequential communication. And I also set up a conversational chain that would take the model and allow it to perform the vector similarity search from the input data. This vector store object comes from text tokenizer. So to allow the model to answer college level chemistry questions in our minimal implementation, we load a PDF from Google Drive that basically stores functional group properties We split it into chunk sizes of 50 and chunk overlaps of 10, and we load the sentence transformer model that converts this into a highly vectorized numeric space for the model to understand. And this allows the model to perform efficient, fast vector similarity search. When the display chat history function is called, we allow the user to ask any small molecule question and have a send button to click. Once the send button is clicked, the model would call the conversation chat function to retrieve the output. And this calls a chain, which would perform the vector similarity search necessary for the model to output the response. It stores the history of conversation and also has an export button. If the export button is clicked, we would store the information in the database for future reference. We also saw how the chatbot supports the visualization of smiles in 2D and 3D. We allow the user to enter the smiles, and when the 2D button is clicked, we basically take the smiles and create an image of the skeletal formula in a certain file path, and we output this image on Shreeman. If it's the case for 3D, we take the smiles and convert it to a PDB format, which stores it from 3D atomic coordinates and the atomic interactivity of each atom with other atoms. It allows the user to download the PDB file, and also it creates a link where the user can access MolView Spec, which is a 3D visualization tool that can take in a PDB file and give out an interactive, clickable, and rotatable visualization of the smiles. Chatbot also supports the exported database subsystem by allowing the 2D and 3D visualizations to be exported to Firebase. We specify the local file path and the remote file directory where we want to store it on Firebase. And in this case, we use the images directory. For the 3D, we're able to store the link of the visualization, the MolView spec, to the database. To give you an example of how Firebase is set up, I'll open up Firebase. My project, this is the real-time database where I'll store the 3D visualization links. If you go to the storage bucket right here, under the images directory, we're able to see that the 2D visualization of aspirin from the chatbot was stored once the export 2D button was clicked. The exported database subsystem stores a chat history, 2D and 3D visualizations for the user for future reference. I had to create my own account for myself, which had a real-time database to store the chat history and 3D visualizations. The storage bucket would store the 2D images in the images directory. To set up Firebase, I had to create a project with the Molecular Discovery Chatbot, and I had to go to service accounts and generate a private key for me to have admin access to read and write from the database and storage. I had to use this file and import it inside Google Colab. To allow the chatbot to connect with the exported database subsystem, I used the Firebase admin open source library. Upload to storage function allows me to specify the local file path of the 2D visualization and store it under the images directory in storage bucket Firebase through a series of function calls. The save to database function, on the other hand, is called to store the download URL on the real-time database, not on the storage bucket. So these are two separate functions that I created to connect the chatbot and database. The visualization subsystem is responsible for creating 2D and 3D visualizations from a smile sequence. So where's your inputs of smiles on the chatbot? What does the visualization subsystem do? It converts a smile sequence first into a mole object. It adds hydrogen atoms to the molecule and computes its 2D coordinates and returns the mole object. It takes that mole object and it basically stores it inside this file path. So basically, it takes the mole and converts it to an image file, which can be viewed on Streamlit. For the 3D visualization, however, we need to convert it to a PDB file which stores the 3D atomic coordinates and interactions. So I had to take the smile sequence, convert it to a mole, and call a series of functions that would return the PDB file. Once I had the PDB file, it can be downloaded and it can be accessed on MolView spec to load the 3D visualization. In the online database subsystem, I integrate data frames from the Deep Affinity lab. And these data frames contain KD values between a compound and a protein, such as dissociation constant value, indicating the strength of the binding affinity. I have the small sequences, convert the KD values to high, medium, and low based on a certain category, and add it to this a new column. I add a textual description to help the model understand how to parse through different elements and columns in the data set. Given that we have the UniProt ID, which is not useful information for the model, I export the UniProt IDs from all the rows to a file, and I use the UniProt ID mapper to retrieve the protein names and organism for each ID and append it to the data frame. I also map the protein ID to the protein sequence itself, which is a sequence of amino acids, and I split the set into training and testing 70% and 30%, and I store it in binding affinity train and test, which is used in both the fine-tuning and the tokenization subsystems. Since the capacity of the default model is reserved to basic chemistry questions, I explored the possibility of fine-tuning the model on the binding affinity data from deep affinity using Colab. To execute this, I started by mounting the Google Drive, which allowed me to import the data from deep affinity and the model weights because they were very, very large files. So I stored all of the data inside my Google Drive account. I installed specific open source libraries and imported them. I loaded the training and testing dataset, and I also used the Llama 2.7b HF model from Hugging Face for the purpose of fine-tuning. This model has 7 billion parameters, and to execute this on a runtime, I had to use a T4 high RAM GPU on Colab. I also proceeded to load the tokenizer. After loading the tokenizer, I proceeded to set up the quantization configuration as 4 bits to account for the memory requirements and memory limits of Google Colab instead of default 16-bit. I also set up the Chlora configuration and proceeded to load the base model itself. Next, I proceeded to process and split the data. So I imported the train and testing data set. I sampled it for however many samples that we want to fine-tune on, and I split it into 5 equal parts so that we can fine-tune the model on batches of data instead of the entire data set in one go because of the memory limitation of Google Colab. An example data set would look like this, with the protein name, organism, smiles, and the UniProt ID in the sequence. And then proceeded to write a function that generates a prompt that guides the model on how to give a response. So the prompt goes, you're an expert chemist, predict the binding affinity, given the smiles, name, organism, follow the format of information provided, answer it high, medium, low. I also appended an instruction with the textual description part of the dataset, so it contains the smiles, name, and organism. I then proceeded to specify the training arguments for fine-tuning, which included the epochs and train batch size and other important configurations. For each training and testing pair, I decided to use a supervised fine-tuning trainer to fine-tune the model on a training batch as the train and evaluation dataset. And for the last iteration, I decided to use the entire testing dataset for evaluation. I saved the model at every iteration to this folder called Hugging Face Test, which would store the model weights of the fine-tuned model. After about 20 seconds of execution, I stored the model weights. I proceeded to clear up memory because we were taking up the entire RAM. And then I loaded the pipeline and I passed in the prompt that was formed by the prompt generation function. As you can see, the output of the fine-tuned model for the given prompt is this. Prompt engineering is the process of performing binding affinity label prediction given a small sequence and a protein sequence. To benchmark our large language model, I created a random model that would randomly generate medium, low, and high labels based on the frequency, the input data. And the accuracy of the predictions happened to be around 42 to 48% for multiple cycles of the data. I'm going to access the model using 20 samples from train and 20 samples from the test. I'm going to executing the function. What the function does is basically provides a prompt to the model that guides the model how to provide a response and feeds the smiles and the sequence from the test in an iterative loop. This feeds the prompt to the model inside this function using a set of hyperparameters, and it writes out the time taken, the response, and the actual labels so that we can calculate the accuracy and validity of the generated response. To assess the performance of our model for educational users, we're going to use an educational assessment called BASE. BASE stands for beta-site amyloid precursor protein cleaving enzyme, which is one of the 8 different comprehensive educational benchmarks that has been well researched. The model basically has to predict whether it's yes or no inhibit, given a smiles string. What we're going to do is we're going to import the base data, relevant data, and we are going to sample. For the case of the assessment, we are going to sample 30 different smile sequences, and we're going to pass the model to make predictions of the base inhibit, whether it's a yes or a no, given the smile sequence, and the prompt, which gives the instruction that guides the response. As you can see, we have a lot of yes, 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 yes. And accompanying with these responses, we also have some explanation of why that base is yes or no, which means that the model is not hallucinating for an educational assessment and it's qualified to answer it. And you can see most of it are yeses, but the actual labels, this function right here, shows the actual labels based on for the 30 different samples, and half of them are yeses and half of them are no's. So you can see the accuracy would be about 50%, but accuracy cannot include hallucinations in the denominator. There were a few cases of hallucination when the model cannot explain why there was inhibit or there does not inhibit, right? Those cases are going to be omitted from denominator, leading to much, much higher accuracy values based on valid answers, which would be about 70%. For advanced research users, we assess the model using a conditional generation assessment benchmark. Basically, we ask the model to generate a new smile sequence that satisfies the binding affinity label. In this case, we allow it to be randomized to low, medium, high because we want cases where the binding affinity stays the same and binding affinity also changes after the modification. We feed this prompt with the instruction on how to format the response together with the smile sequence and the label to the model. This is a model without any sentence transformer included, and just the model itself. And we also record the time and the response into an output file. The model is assessed over 50 different test smiles. Calling the function, we generate a range of responses, some of which includes very clear explanations on why the binding affinity label changes in this way. For example, with this case, where the response is this smile sequence, we replace the nitrogen atom with covalently bonding oxygen atom to increase the hydrophobicity. We also add a methyl group to further enhance the properties. There's some cases where the model hallucinates and it's not able to generate the right smiles, but sometimes it's able to explain, which means that the model is technically not hallucinating. After running the conditional generation assessment, there were 7 different responses that did not include hallucination. Out of those, 3 of the responses had valid smile sequences generated. We proceeded to use the cache pipeline from Deep Affinity to calculate the binding affinity between the generated smiles and the protein sequence. This was one of the valid smiles, sequence 1, smiles 2, sequence 2, smiles 3, sequence 3. After running the cache pipeline for pair 1, we generated these PKD values. For pair 2, we generated these PKD values, and for pair 3, we generated these PKD values after analyzing. And we noticed that for pair 1 and 2, it correctly identified medium and medium solubility, and for pair 3, correctly identified high solubility, which indicated an accuracy of 100%. The large language model subsystem has a very limited understanding of smiles. This processes them as text. Smiles contains important structural information, interactivity in the presence of functional groups, which is not captured. And that's why the tokenizer subsystem contains open source libraries like SmileSpeed, which which allows these small sequences to be parsed at a fragment level to identify key functional groups. These libraries are trained on SmilesP. These libraries are trained on Smiles vocabulary. The tokenizer subsystem builds upon an atom-wise tokenizer using a mask-based tokenizer for Hugging Face. This allows me to replace a fragment within the Smiles with a new fragment, allowing for unconditional generation of Smiles. To allow the model to be trained at a fragment level rather than an atom level, I use SmilesP's vocab list from KBL, and this contains pair encoding of different small fragments based on their frequencies to identify the presence of functional groups within Smiles. This is stored in this vocab file. I updated the tokens of the mask-based tokenizer with the tokens from SmilesP to allow for fragment level tokenization. To perform mask-based tokenization, I converted the Smiles into a numerized form, and I called the mask-based tokenizer to generate a new token to replace one of the fragments with. And this time, I split the Smiles using SmilesP vocabulary and allow a randomized replacement. And then proceeded to calculate the TAMU similarity of the input and output Smiles through getting the Morgan footprints of the input and output Smiles to ensure that the input and output Smiles were fairly similar, or minimal editing was performed. I also calculated a validity score using an RDKit function to see if the final Smiles was valid. And I outputted them into a dictionary. And then proceeded to generate 100 Smiles for each of 20 random Smiles for the purpose of the assessment and store the results in output.txt. So for example, I passed in the Smiles, which basically performed different types of randomized replacements at different positions in the Smiles sequence. And I noticed that Smiles inherently has nested parentheses, so when I replaced it with a random token, it led to orphan parentheses, which undermined the validity. Regardless, we obtained a validity of 27.2% and a similarity of 78.49%, which agrees with our validation. Thank you very much for watching my final demonstration.